Hello, good morning, everyone. So yeah, today we have our second webinar for the Frontiers of Biomedical Imaging and Analysis webinar. Yeah, it's great we have Dr. Daniel Rubin to be our speaker today. Now I'll let Dr. Koskin to introduce our speaker for the day.
Hi, everyone. Welcome to our second webinar series. Today, we are very happy to have Dr. Daniel Rubin from Stanford University. And Dr. Rubin is currently a tenured professor of biomedical data science, radiology, and medicine at Stanford, and director of biomedical informatics for the Stanford Cancer Institute. His NIH-funded research program focuses on artificial intelligence in medicine and quantitative imaging, integrating imaging with clinical and molecular data, and mining these big data to discover imaging phenotypes that can predict disease biology, define disease subtypes, and personalize treatments. And he's a fellow of the American College of Medical Informatics, fellow of the American Institute for Medical and Biological Engineering and College, and distinguished investigator in the Academy of Radiology and Biomedical Imaging. And Dr. Rubin has contributed to many papers and patents for his work at Stanford. And without further ado, I'd like to actually turn to Dr. Rubin and welcome him again. Thank you. You're muted, Dr. Rubin. At the bottom on the left side, there's a mute button.
You can hear me? Now can you hear me? Thank you for pointing that out. All right. Good morning, everyone, or wherever you are in the virtual world, time zone-wise. I'm going to be talking today about methods for making AI scale, become more robust for medical applications and imaging. I'll talk a little about the exciting things, but really want to focus on some of the challenges and paths forward. I want to thank both of you for introducing me, and happy to be here and talking in this venue. Most important, I want to acknowledge my lab and my collaborators shown here. I'll be showing work.
Sorry, 1 second. It seems actually the share window is gone. Maybe
Did
because
we stop sharing?
Yeah, we stopped the practice session.
Okay, let's try it again. Yeah. Are we sharing
Great.
now?
Yes, perfect. Thank you.
Okay. Listing here my students, postdocs, and collaborators, and funding from NIH and from some company support. I have no personal financial conflicts related to what I'll be talking about in this talk. So what I'll be reviewing is first an overview of some exciting things going on in AI, but then I'm going to spend most of the time talking about some of the key challenges that could mute some of that excitement. And I'll be talking about these three key challenges: integrating multimodal data, not just doing AI based on images alone, making AI models more generalizable, probably one of the most important weaknesses currently, and the need for clinical evaluation and post-marketing surveillance once an AI product is out there. So just to kind of show how much excitement there is out there in terms of AI development, the ACR keeps a website of FDA-cleared algorithms, and when I last went there like a week ago or so, there were 110 FDA-cleared algorithms, most of them relating to medical imaging. So that just kind of shows the excitement. And if you go to the RSNA, I mean, RSNA last year had like 250 AI vendors in a whole separate area. So there's a flood of these applications. So speaking of floods, they kind of get divided into upstream and downstream areas of work. It's most people, when you think AI, they think, oh, radiologists looking at the image and improving their interpretation, but there's a whole slew of applications that happen before the image is even acquired. That's the upstream thing, and that would be things to improve the efficiency of scheduling an exam or protocoling the exam once it's a technologist is going to do the scan. Just the workflow of moving the image data around the department, and certainly a lot of exciting AI development in automated reporting or pre-filling radiology reports. And almost most of the AI work in the upstream area is image processing, enhancing the image, and particularly leveraging low dose data to generate the equivalent of high dose. That's actually, I think, where most of the impact we're going to see in the shortest term is. Then the image is, once it's acquired, flows downstream to the radiologist. And these are all the applications that people are talking about in terms of assisting detection of disease, segmenting it for making measurements, diagnosing it, and assessing or making predictions about response assessment or future clinical outcomes. So that's kind of one slide overview of like all the applications. One thing I want to focus on, I'm going to be focusing more on the downstream. And in the downstream parts, well, even in the upstream, the image is like the center of the action. I mean, that's where all of the activity is just AI consumes the image. And I want to emphasize in this talk that in terms of the challenges, not all the use cases can be satisfied by just looking at the image. Other data needs to be brought together, which brings up the need for multimodal models. So the kinds of things that are amenable to just image only input would be image enhancement, so that upstream AI application, and disease detection, lesion or disease segmentation and measurement and diagnosis. That's all perfectly fine for image-based development. But these areas, selecting the optimum treatment, response assessment, and clinical prediction, need integrative models. You need more than just the image. I mean, there are some works where they're making predictions based on only the image, but there's a lot of valuable information in complementary sources, particularly in the EMR or in monitors or in genetic data, that when you integrate them with the image data, generates much more powerful models. In terms of clinical impact, I'm very interested in these three areas because clinicians have a hard time with this. Most clinicians are okay. I mean, image enhancement is, put that aside, but detecting disease and diagnosing it and measuring it, something clinicians can do pretty well. I mean, there's some argument you can improve performance, but here there's just huge gaps. And I'm very excited about the applications that will come down, that will be involved in these downstream applications, but they require more than just the image in general. So I want to focus the rest of this talk on the key challenges, because just whenever someone shows you an AI application, questions you should be asking would be, is the model using enough input data? Is it sufficient just to use the image data? How generalizable is it? And how well is it working in actual workflow? I want to first talk about integrating multimodal data. So when I say multimodal, I'm talking about images and some other data associated with the images. Multimodal could be just images if you talk about combining different modalities like radiography, CT, and MRI. Those are different image modalities, and they are complementary. So that would qualify as multimodal. And also would qualify, would be combining the images and annotations or markups that radiologists make because they're adding knowledge, to the images. Now, when I'm talking multimodal, I'm really referring to combining images, and it could be multiple different modalities with some other completely different imaging modality, in non-imaging modality, such as EMR data. And the EMR data, there's subtypes of that. There are structured values, like laboratory values, which are structured, vital signs, demographics, genetic information. And then the clinical notes, which are narrative text, which are unstructured data, just like the image data are unstructured, which brings up its own challenges in terms of how do you integrate that. And in addition to that, there may be other data that's not in the EMR that one might want to integrate to generate a robust model. I emphasize the need for considering multimodal data in AI models because clinicians consider all relevant data when they're evaluating patients. They don't just look at one thing in general. And so our AI models should similarly be doing that. And there's much less work in that space. And most of the current published work, as you look at, you'll see it just uses one type of data. So just to show the contrast, this is a typical AI algorithm to make a diagnosis or do a detection from an input image, and all you need is the image, and the output would be trained to recognize imaging findings. So that'd be a classical neural network, and that's a lot of what the current imaging applications are focused on to, for example, fill out pre-populated radiology report. But if you're going to move to integrative models, then you're going to need more complex architectures such as this that would include one or more modalities of imaging plus EMR data, and then combine those in some way. And I'll talk about that in a moment. But the there's going to need to be, we can deal with input image data, but to input the text data, you need a way to generate a representation of that text in order to generate features that can be accommodated into network structures similar to the images. And a very powerful method that's dominant now for generating a representation of text for input into AI applications are word embeddings, which, for those who aren't familiar with this, bag of words were the traditional model of representing words as document vectors, where each dimension of the vector represented a word. In a word embedding, what you do is you learn a space where each dimension of the vector is not a word, but a number that represents a representation of the word and its context, which is learned in a large unsupervised task of looking at, you pick a window, let's say 5 words surrounding each word in text, and develop a representation that takes into account the word and its corresponding words nearby, with the concept being that the meaning of a word is represented in conjunction with the words that surround it. The lore is a word will know its meaning by the company it keeps, the words that are in close proximity. When you look at this example, the words in blue kind of do have some relationship in terms of meaning to the red word moon, and so we could put moon into a feature space that's determined by those correspondences. And when you plot out other words in the same space, words that have similar meaning tend to cluster together. So it's a very useful representation because now it's based on the semantics. And once you transform, so every word is a vector, and you put all the words in that vector space, you can now do nice things. Like you can cluster the words and find similar meaning words, but more importantly, you can take the representation and do things like use that as your input for your input representation for text, and now go forward and do, for example, a classification task, classifying a report as positive or negative for describing certain findings. So this is now a very popular methodology for information extraction or document classification. By the way, you can also generate embeddings of images. So just like we took raw text and generated an image, a representation of the text in an embedding space, you could do the same thing with images instead of working with the raw images. But once you've got an embedding representation, the next thing is you've got to merge the different modalities. And a common way in which one will do that is, let's say this is an embedding space for the text, and this is an embedding space or the raw image data. We could concatenate the two and then feed it forward into our network and train it to for a particular task. Another possibility, though, for fusion is you could have separate models that take those inputs separately and then have a voting scheme or some way of integrating the two outputs of the model to generate a final result. And you can even have different flavors of intermediate fusion. And so this is an active research area, is what's the optimum model for fusing multimodal data. And this model, you generate an end-to-end set of weights for this intermediate fusion, which comes with some computational costs. So there's trade-offs of these. I'd have to say the early fusion generally is the commonest method that people are doing. And just to give you an example of the value of this, and I'm going to also add one more thing, which is longitudinal data to it. This is a multimodal fusion. It's early fusion. We're fusing an embedding representation of the image features with demographic features. So the image features are represented in blue, an embedding of the image data plus the demographic data. And then we've got a feed-forward neural network to make a prediction. The goal here is these are eye images, patients with AMD, age-related macular degeneration. And the goal here is a small percentage of those patients progress. We want to predict, are you going to progress within 3 months? Because if the patient will progress, they should be carefully screened for rapid progression. They're at high risk to have their disease rapidly progress to blindness. And by triaging them into a high and low risk category, we can pick up that progression sooner and institute therapy sooner. Now, in order to make a prediction test like that, we could predict based on one time point, but it turns out the performance of a model when you just use one time point is okay. It's not terrific. I'll show you that in a second. By using an LSTM model and the fact that patients come and see their eye doctor like every year, there's features in the longitudinal evolution of subtle changes in these images. So we basically have the same model at multiple time points, but now we have weights between the time points. And this LSTM, long-term short-term memory network, is learned against a historical set of training data where we had multiple prior visits. And then for every patient, when they come back to the doctor, we look back, the model looks back at all the prior visits and incorporates that in terms of the prediction that it makes. And just to show you the value of this, of one time point versus multi-time point, this is the ROC curve. If you build a model, and it was a random forest, but would be similar performance if it was a CNN, multimodal CNN, just with one time point. You get, an okay ROC. But if you use the LSTM model, multimodal with longitudinal data, the predictive performance shoots up dramatically. So this highlights, and of course, if we just use a single modality, performance decreases. So take home message here, multimodal models, and particularly integrating longitudinal dimension of the data, highly valuable for generating a predictive model. So we want to move toward multimodal models, and particularly models that incorporate multiple time points if available. Downside is you need to get your hands on all that data. Now I want to talk about AI generalizability as another challenge. No matter what model you build, someone will show a nice graph like I showed in my last slide. First question you should ask is, well, how well will that work in my setting? There was a very nice paper that came out a few years back, that I cite at the bottom of the slide, to look at the challenge of AI generalizability. The task was, let's look at models trained on different subsets of chest radiographs. Three different institutions, NIH, Mount Sinai, and Indiana University. The task was detecting pneumonia, so binary task. And they trained this model on different subsets of these data and tested on other subsets of these data. So here in this slide, these are the different training, and they did training on just NIH, on just Mount Sinai, or the combination. And then they had different test sets shown here. You don't have to scrutinize these numbers too much. The main thing to look at is these are the different metrics of performance of this binary classification task. And you can see that the numbers vary a lot depending on what the training and the test sets were. And so that shows, and we all know that everything in a deep learning model knows, it learns from the data. And to the extent that data are heterogeneous and non-uniform across sites, you'll get a model that performs variably well, depending on how representative that data is for data at large. So how can we overcome that problem and make our models more generalizable? There are a few major ways. One way is, well, let's just get more data. It's costly to acquire a lot of quality annotated data, as we know, and there's a number of works underway to just leverage unannotated data. It exists. There's tons of unannotated data, so that's cheap. But when you leverage unannotated data, you're going to generate some kind of an annotation programmatically that is noisy. That's called weak learning. Another strategy is to remove low-value training cases. And a third way is to leverage quality annotated data, but from many, many sites. And so through methods like federated learning. So I'm going to talk about these three strategies. Weak learning first. So the concept here is get your hands on a lot of unannotated data and use methods to weakly label them. Now, what is a weakly labeled example? Well, every image in radiology is associated with a text report. So you could write some simple rules to go over the reports and put labels on the images from terms seen in the report. So we admit that those labels may be weak because the text processing algorithms may not take into account things like negation or synonymies or other variants of words in text. But once you do that, then you can build a model on top of those weak labels first, you could clean the weakness in the weak labels by looking at discrepancies in labels, and that's done by making a generative model, and then using that to produce final labels. Still, the labels are weak, but it's just to show you the power of this in a large scale. We did some work with a large chest X-ray data set, and we wanted to leverage unannotated cases to do a classification of normal or abnormal. There's many different kinds of abnormalities. Here's a few of them shown here. lung mass, cardiomegaly, pneumonia, and pneumothorax. And every case in routine radiology practice has a narrative text report. And so what we did is we had different amounts of expert labeled or high quality labels, EX. Those are shown as the solid lines. What we call clinical labels are the programmatically noisy labeled cases by writing those rules over the text reports, and those are shown by the dashed lines, and in different amounts, 2,000 cases, 20,000 cases, and 200,000 cases. So if you train a model with 2,000 cases and with high quality trained labels, you get a curve that's shown here with the arrow. And if you use a weak learning method, 200,000 cases trained with these noisy labels, it was no more cost to us. So we just ran this code over our unannotated labels, unannotated cases. We get superior performing a model. Now, obviously, you can do even better if you have larger amounts of quality labeled cases, but we can certainly improve. Most studies are using on the order of 2,000 cases because it's very costly to get quality labels. So the more unannotated data you have, however, the higher the performance you get. And we've done this with different use cases besides chest X-ray. So leveraging unannotated data is definitely a good way to get both broader representation and better performance of models. Another way of making models more robust, instead of trying to go for getting your hands on more data, is you could employ some techniques to identify data points that are degrading the performance of the model. We've done some recent work in collaboration with James Zoe on using a metric that came out of economics called data shapely, which quantifies the value of training data points in a model. And the metric is basically a real number, non-zero, with a positive value indicating that the data point contributes positively to the performance of the model, and a negative shapely value is detracting from the performance of the model. Don't have time to go into the details. I can send you a reference if you're interested, but the critical results I'm showing on this slide, where we're plotting we have a data set of hundreds of cases that were trained, and we had different amounts of training data that was removed, where we're removing high value data points. So as we remove more and more of the percentage of high value data points measured by the shapely value, the performance of the model, this is the prediction accuracy of the model, starts out at around 52%. It's an average performing model, but it starts dropping down to around 35% as we remove more and more valuable data. Now, one would obviously not want to do this in practice. What one probably would want to do is, well, what if we start removing the low value data? So we started, around in the 50s. And as we start removing more and more low value data points, we start getting closer up to we start reaching a plateau around 70%. So by just identifying the value of individual data points, it's sort of a way of denoising your model and improving its robustness. The third method I want to talk about comes back to getting your hands on more data, but getting your hands on quality data as opposed to weak label data. And so since many institutions do have quality label data sets, probably the simplest thing is, well, let's get them all to bring those together into centralized data sources. And there are efforts funded by NIH and other support to make such centralized databases, such as the Cancer Imaging Archive, Imaging Data Commons, and the MIDRC COVID-19 resource. The problem is that those span a limited number of diseases, and there are many problems that they aren't covering. And hospitals, won't voluntarily share data because of concerns that I'm showing here. So for use cases for which we don't have large centralized data collections that span many institutions, the paradigm of federated learning is emerging as a popular paradigm. The concept is, instead of bringing the data to the model, if you imagine you've got a central AI server and you've got several hospitals, get them to share their data on a central server and then build your model. That's the centralized method. Instead, send the model out to each of the institutions. They've got to have a GPU machine, but then they would train their model on their local data, and then you would have some mechanism, and this I'm going to emphasize, there's many ways of doing this, some mechanism to aggregate those models. That's actually an active research question, how best to do that. But by doing that, we're just sharing the model, not the raw data. Now, there's potentially a privacy concern here. It's because one could theoretically reconstruct the raw data from the model. So there is another layer of this that's needed, is a privacy protection mechanism for either homomorphic encryption or differential privacy for sharing this. We can talk about that separately, but the concept is at least we're not sharing the raw data. And one could always start with de-identified data at each hospital, but the data isn't leaving the site. Now, the concept is nice, but there are a number of the devil's in the details, as they say. There are still active problems that hinder this from really taking off. Well, the first one, and this first one is actually common to the paradigm of centralizing the data too, for that matter, is there need to be standards for the image annotations. And if people use different terminologies for the same thing, it's going to be difficult to leverage those data, whether you centralize or federate. But standards for how you save those annotations and the terminologies you use are critical. I mentioned that there's more than one method for distributing the computations. That actually has a big impact on the final result. And a very important point I want to emphasize is variability in data across institutions. In classic federation, where you have all the data and you're going to parallelize the processing, you tend to just break up the data sets into independent, identically distributed IID distributions and do your computations across the distributions in a parallelized way. Here we got the reverse problem. The data is already distributed, but it's not necessarily distributed uniformly across the hospital. So when we do the local training and then aggregate the results, we do not necessarily get the same result as when we combine all the data on a central server. And that's what I refer to as variability of data across institutions. There are other issues. I'm not going to have time to go into these, but these are other important issues that come up as well to make federated learning work. So I'll go through the top three ones. So data standards, you need to have data standards for interoperability, because you need to interoperate amongst both the formats in which the annotations are saved and the content, the labels. So the regions of interest, if someone has ROIs like arrows or measurements, these need to be represented in some standard way so that you can merge the results. The algorithm can operate them consistently on the different sites. And the labels need to conform to a standard terminology. So you need a standard terminology that all the sites agree to, like RADLEX or SNOMED, for labeling diseases or imaging findings. And then they have to save those annotations, the regions of interest that are drawn like measurements, and these terms in the annotation in a standard format. And there is a DICOM format called AIM DICOM T80 1500, which is important to be familiar with. That's less familiar than DICOM. The AIM standard came out of the NCI program a number of years back, and recently it's been incorporated into DICOM as a standard template, which is beginning to be adopted, but not widely. Still, most of the deep learning work, people are not using these standards, and so that's the first thing people have to do is harmonize. We've been developing tools to facilitate this. We have a freely available open source web-based viewer, like a PACS, that supports these standards. And so if sites use this to annotate their cases, it saves all of the annotation information, measurements, terms. It supports RADLEX. It saves this in a standard format. So you've got an RO, if you have an annotation like this, and you've got labels, or if you want to make specific descriptions, you can create these templates, and they support controlled terms. And if you have quantitative features, EPAD will save those as well as the annotations in this DICOM compliant AIM standard format. And then if sites are all compliant with that, then we can just run federated learning across all the sites immediately without the need for any data conversions. The next thing, besides standards for terminologies, is how are you doing the aggregation of the models? I mentioned earlier, there's more than one way of doing that. The commonest way, which was the first way Google came out with, is called model averaging or ensembling, where you average the weights of the models. But that's not the only way of doing it. There are weight transfer methods and these other methods, which I don't have time to go into in this talk, but I have references. There's many ways of actually doing this, and they have an impact on the final result compared with what the model would have been if you trained with centralized data. So you don't necessarily get the best performing model by just simply picking any particular one of these. You need to actually study them. And we've been doing that. We have studied the ensembling or model averaging method. That's this B method, where you train a model at each site and then aggregate the coefficients, average them to generate your final model. And we've looked at weight transfer methods, where you train at one institution, send the trained model to the next as a pre-trained model to then train on its data, et cetera, and then take the final model, or do that cyclically until convergence. And we've compared the performance in these scenarios with centralized data, which is a case where that's the best you can do. That will be the best performance, because if there's variability in the data across these sites, that won't exist when you centralize. Whereas if there's variability in the data across these sites, you'll get different performance. And we actually compared two scenarios where the distribution of the data is identical across the 4 sites, and when the distribution of the data was not identical. So let's start with the identical. In this case, we're comparing the different methods here, these 3, against central hosting, and the distribution of data is identical across the 4 sites. And in that case, the methods do not perform the same. The ensembling, model averaging, performed the worst compared with weight transfer. And furthermore, when you add more and more sites or more data, you get closer and closer to the maximum performance that you could get if you had centralized the data, which is intuitively obvious. But the more important point is the method by which you do the federation has an impact on the final result. That's one dimension. But I remember I told you that the data is identically distributed across the multiple sites in this scenario. What if the data is not identically distributed, which is actually the real world? It's almost never going to be the same, because hospitals have different numbers of patients. It is different distribution of normal and abnormal and variabilities in other factors. And as I said, in classical federated learning, we've got control over the parallelized splits. But when we do federated learning in medical data, we have no control over that. And now I'm going to show you that the impact of heterogeneity is to degrade the performance of the federated model, regardless of the method you use to do the federation. So I showed you in the earlier slide that the the cyclical transfer method did great. It almost did as good as centralization, and that's over here on the left, where we have central hosting and our cyclical weight transfer. The methods are very comparable performance. But as we introduce more and more heterogeneity across our sites, this is sample size heterogeneity, the performance of the CWT method significantly drops. I mean, the absolute numbers aren't gigantic, but the differences are statistically significant. And also, if the distribution of the labels across the sites increases, the x-axis is more and more heterogeneity across the sites, the more the decrease. We have been working on methods to overcome this variability. One can do that by taking into account, in doing the federated training, local variations, looking at how many cases and distribution of labels do you have, and taking into account through a variety of different methods to refine the training to account for those variabilities. We've been focusing on so far variability in sample size and variability in the label distribution. So we'll go back to those 2 graphs and add in, now we got black and gray for the original graphs, and we've added in 2 different methods for trying to account for that variability. And you can see that's starting to improve the performance. We still don't get, for both sample size heterogeneity and label distribution heterogeneity, we're recovering some of the performance, but still not completely recovering what you'd be at in terms of central hosting as you introduce more and more heterogeneity into the across the sites. So the bottom line is heterogeneity exists in the real world. It degrades the performance of federated learning. Methods need to be developed to optimize and take into account these variabilities. And we've been doing some more recent work, which is in press, that we've actually now gotten to recover all of the loss. But it's still an active research area. And the final thing I want to talk about is we will do various things to improve our models. But if we think we've done really well, we're still not done. We need to evaluate this in the actual real world setting and undertake post-marketing surveillance, because everything an AI system knows is just based on the data it's trained. And no matter what we do to try and improve the representativeness of our models, whether it be through weak learning with unlabeled data, a lot of unlabeled data, we're still working with data from one institution, or if we use federated learning, we use multiple institutions, but they still may not be fully representative of all the institutions out there worldwide. And therefore, they may not generalize and work well on the new data. So no matter what we do, I do believe that anyone who's going to be implementing or using any of these things in practice needs to have an approach for testing and monitoring on an ongoing basis how well it works on their actual data. Notice I say and monitor, because if you test it once and your population evolves over time, and certainly your equipment will. I mean, look at what's happened with medical imaging. We've gone to thinner and thinner slices. As soon as that happens, the model performance may be completely different. So we have to have a continuous process of testing and monitoring. This is not too dissimilar from what physicians do in terms of their medical education, continuing medical education. We're intermittently testing and monitoring how well clinicians do, or at least through continuing medical education, to ensure quality. And I think we need similar processes for AI. In the imaging world, what would that look like? This is sort of the image workflow without AI. The image acquisition system generates the image, makes it available in the PACS. The radiologist looks at it, generates a report that goes to the radiology information system. When you introduce AI, the image also goes to the AI, it generates its result. It might put a circle on the image for an abnormality. The radiologist will look at that and generate a report. And they'll consider both the AI and the result without the AI. If we want to monitor the performance, we need to have some way of establishing the gold standard. In some cases, the radiologist can be the gold standard. If the AI is doing a detection task, like is there an abnormality in the image, the radiologist is sort of the gold standard for that, although there's variation in practice amongst radiologists, but that's about as good as we can do. And then if it's a diagnosis, we have to go into the medical record, but there needs to be some process, whether it uses the medical record or just the radiologist or a combination of the two, to establish a ground truth that then can be agreed or disagreed to in comparison with the AI output. And that needs to then be factored into the final report, so that a final report is generated that will record the final, but a diff needs to be done between that final report and the preliminary report to capture the errors that the AI made. And those errors can be reported to a registry, and the American College of Radiology is in the process of setting up such a registry. But if all the practices had infrastructure for recording these deltas, corrections that radiologists made as part of the routine clinical care to the AI outputs, and we recorded that in a registry, that would be of immense value, because that could be fed to the vendors of AI systems to retrain their algorithms and improve them. And could also be used to help educate radiologists in terms of being wary of cases. What are the common cases where the AI fails? When can you trust it? When can't you? But without data collection around how well they perform in practice, we can't get there. I showed you the EPLAD platform earlier. We've been using the EPLAD platform to record those deltas, so that if an AI algorithm generates lines and the radiologist says, no, that's wrong, and they correct it, we record those deltas and differences between the initial report or result and the final one, and can populate generate metrics for performance off of the AI and feed them into a registry. So just to conclude, I made three major points in this talk. First, although most of the AI development is focusing on just the images and input, I said that many use cases really require multiple pieces of data to be integrated. That's what clinicians do, and computers need to use multimodal models in many important use cases to really perform robustly and help with clinical decision-making. For some tasks, image alone is fine, but for many, you need to have that integrated information. So that's a challenge, because you need to get your hands on multimodal data. Getting hands on a lot of it can be challenging, but it's needed for training AI algorithms for many applications. There is a challenge for making models generalizable. And for that, I talked about three different approaches, with using weak learning, with using federated learning, and identifying cases that have low signal or low value, with the data shapely as an example metric. And no matter what you do, at the end of the day, you need to evaluate your model in the actual clinical workflow and monitor it in order to assess how well it's working. And there are tools that are being developed, at least we are working on, and hopefully others will develop to facilitate doing this in the real world workflow. So with that, I'll end. I thank you for your attention. Happy to answer any questions. Thank you.
Thank you, Dr. Rubin. Go ahead, please, Pinkham.
Yeah, thank you very much for the great talk. I saw there's already one question posted to the Q&A session. So here's the question from Abbas Chadard. I just wonder how much trust acceptance AI is making among radiologists and medical staff, non-tech.
Yeah, so it depends on the task. I mean, for some tasks, the radiologist, by the way, did you finish the question? Is that the full question? Did I cut you off?
Oh, yeah, that was a full question. Yeah, it's
Okay.
in the Q&A section.
So I talked earlier about upstream and downstream AI applications. For the upstream applications, radiologists are probably not even going to be aware because the algorithms that enhance images, like create normal dose images from low dose images, the radiologist will not be even aware because you'll get an image. In fact, you're not aware of the reconstruction algorithm, with the kernel, which kernel was used. I mean, there's a lot of this that's getting into the upstream part that's pre-radiologist. Trust is not unreasonable there, though, because you could, there's been some work to show that it's possible for these methods to hallucinate things when they're generating these images that don't exist because they're trained on lots of historical cases. That's certainly worth wondering about. But most of I think most of the questions about the downstream AI applications, like an algorithm that will make a diagnosis, when can I trust it? And this is a critically important area for a couple of reasons. First of all, the generalizability issue we talked about before, but more importantly, the issue of bias. There's been a lot of work that's coming out showing that most AI algorithms are biased because the populations in which they're trained have insufficient representation of minorities. The facial recognition, a very good example. And you're not going to be aware of that when the AI is performing unless there's some specific tests done to see how well do they perform in these different patient subgroups. Another challenge is few algorithms produce a confidence factor. They just produce a result. I am a strong believer that algorithms, when possible, should produce some sort of a metric of equivalence of a confidence score, a number that indicates how strongly does the algorithm believe that it's right about this. Because if a radiologist is given a recommendation by the AI algorithm and their experience is they take it to be 100% true and then they find out it was wrong, they're going to lose all their trust. And it doesn't take many failures, particularly a bad failure, to lose all trust. It isn't any different than a human being. If you show a colleague's film and they say the wrong thing, you're probably not going to go back to them and you'll remember that, especially if it was an easy case. So trust is a tricky area for AI. I think that for some algorithms, like for those that are doing work list prioritization, this is an abnormal, read this first. Those are performing incredibly well. I think trust, the issue of trust also relates to risk. How risky is it if I trusted it and got it wrong? I mean, with ranking the reading list, as long as you read all your cases, there isn't going to be patient harm if it gets a few wrong and you read a critical case a little later. You'll still probably want to use the AI. But if it's like if it's a CAD in mammography is a good example. In the early days of CAD, they had a high sensitivity and a poor specificity. So there were all these false positives, and radiologists lost all their trust in the algorithms, and it's just taking more time than it's worth. So now they're a lot better, and there is trust that's being gained. In fact, in the UK, the AI systems for mammography lesion detection are sufficiently good that the National Health Service is accepting AI as a second reader. And the NHS requires all mammograms to be read by 2 radiologists. Now they're accepting AI plus 1 radiologist. So it's a function of the use case. I don't think we're going to see that trust gained broadly across all use cases, because some things are just really challenging. You know, imagine an AI to detect, to give you a chest X-ray diagnosis, you know, to take all the diagnoses. You'd need incredibly good performance across all diagnoses, and not all diagnoses are common. So on the other hand, a pneumothorax detector, I can imagine that being very reliable. Sorry, that was a long answer.
Yeah.
Hopefully it answered the question.
Great, thank you. Yeah, I do agree that actually the confidence score from the AI algorithm can definitely boost the confidence of the users. Right? So yeah, great point. Thank you. Actually, we have two other panelists, Ahmed and Marius, Professor Marius Ningraru, also online. Can you guys actually maybe read the following questions?
So I see only one of them.
So in the chat window, there are also a couple of questions.
Oh, okay, in the chat window. Okay, let me kind of see. Somehow I can't see them actually. Yeah, my screen doesn't show up, unfortunately.
Oh, okay, yeah.
Yeah,
never mind. So yeah, I can read the question from Patricio. So the question is that what about the opening of a black box? That is usually an issue when using AI. Which is the current advances or frontiers in biomedical imaging in this direction?
Not much. I mean, right now, the opening the black box is done through saliency maps that kind of highlight the areas where the strongest weights in these deep learning models lie. That is for image only models. We've done some work when you have multimodal models. Now it's very complicated to create the equivalent of a saliency map because it's a combination of information in the text and in the image. And how do you make a saliency map that's meaningful, that says it's a combination of this information in the image and that information in the text? We've been working on some models to generate, you know, which word dimensions of the word embedding space carry the most weight, and pointing that back to words. It's not very satisfactory. What is satisfactory is pointing to a note and saying this note was a strong signal that we did a predictive model, for example, of patient survival for the goal of informing when there should be a discussion of palliative care initiated. And we could point to particular notes or time points in the patient's course where that was a strong signal that was influencing the decision of the model to say it's probably a short-term survivor. And then you could look at the note and see, well, what was it in that would be alarming or suggest that the patient won't do well. But it's not very granular information, and the saliency maps and the image is not very granular. If you've looked at them, they're kind of these fuzzy diagrams, and it kind of varies in terms of quality. You often have hot areas on these saliency maps that aren't necessarily that informative. So explanation, I'd say, is a major weakness of AI algorithms, but there are people who make a good point that do you always need explanation? For example, you don't necessarily need to know how your car drives to be getting in it and driving it. What's really important is reliability. How does it do its thing reliably? People trust the auto drive mode, but now there's some examples of failures of the auto drive mode, so you should pay attention. I think AI is going to kind of go that way, where people will still use it without necessarily understanding the inside of the black box, as long as it's performing well consistently. And not steering them off course. I think that there's a lot of education, though, that has to be done for people to know when should they be aware of it steering them off course. That's why that confidence factor issue is a good example. The biggest issue in that regard is, you know, the AI has to be aware of when it could be going off course. Like if it's seeing a case that wasn't part of the distribution of cases on which it was trained, then it should not interpret that case. Now, a clinician won't be aware of that, but the AI algorithm is, and we're working on that, detecting out of distribution cases, and other people are working on that. That's, you know, one of the other popular areas to work on. But yeah, so I think the black box thing, there may be work that will provide more explanation, but I'm not sure we always need explanation.
Yeah, that's a great point. I think Jeff Hinton also had a similar view. So he said validation could be more important than explanation at some point.
Yeah. It also depends on the use case. I mean, I think, so for example, for AI that's detecting something and puts image marks on the image, you don't need explanation. You look at it and you say, do I agree there's something there or not? If it's going to give a diagnosis or if it's going to give a prognosis, well, yeah, you better have an explanation. Like it says, you're going to die in 3 months. I think you'd want to know, why is it saying that? So depending on the use case, I think explanation is more or less helpful.
Okay, great. Thank you. Let's move to the next question from RB. Can you comment on the potential role of GCNs combining medical imaging and clinical data? I think GCNs probably refers to graph convolutional networks.
Oh,
more
yeah,
related to your first
topic.
point.
Yeah, there's so much one can talk about. Yeah, so graph neural networks. Yeah, so now we're into the framework. Okay, what are the best architectures? Yeah, I talked about vanilla, so that's so passé. There's so many exciting things going on. This field's moving so fast. Like there's self-supervision. That's another thing we should have talked about. Transformers in terms of, word embeddings is kind of old now. There's transformers. Graph neural networks. So yeah, an exciting architecture for certain applications. I think it's a preferable representation. We're doing a project right now where we're trying to automatically detect seizures and localize them. And in a EEG, from an EEG tracing. So in EEG, you have all these probes all over the head, and they have standard spatial placements on the head. And the representation, we've used different models that performed, adequately okay, but we're getting much better detection and particularly localization information by using a graph neural network representation, because in the graph, you've got representations between, you can look at co-occurrences or correlations between different channels of information. I think the original work in this came out of looking at traffic lights and the patterns of traffic lights, which are spatially oriented. So, very cool method. I think not necessarily suited for every problem, but for certain problems, definitely worth exploring and using.
Okay, all right, thank you. Next question from Abbas. So here the question: the major manufacturers of medical devices keep generating new versions of their machines, also including software updates.
Yes.
So how would that affect already trained large models?
Yeah. So that brings up the interesting and very important thing of, or you could say it's philosophical, a question of, should we have one model for all sites? Or should we have, so I'll call it the Uber model, or should we have a single model, a unique model at every single site? And so there's 3 different paradigms. You could say, well, every site, the model at every site should ideally be trained based on the data at that site. You don't have to worry about generalizability. You've got a site-specific model. That's one paradigm. Another paradigm would say, hey, we'll train a model that uses data across all sites, like with federated learning, and we'll do all the fancy stuff we can to get a model as good as if the data had been centralized. So that's an Uber model. And then the third paradigm is, well, start with that Uber model, but then do local refinement, like incremental learning on the data at each site. So we've actually been comparing those 3 paradigms. And when you look at the performance of a single Uber model across all sites versus site-specific models, the Uber model does better. And we've done a few different use cases. But the Uber model will do even better if it's then locally refined with the data at each site, if there is substantial heterogeneity in data across sites. And that point about, equipment change, and then the next thing is equipment changes. Do you need to retrain the model at that point? So that's the issue of monitoring. You need to monitor the performance of a model, and we do need to have a way of incrementally refining the model. Now, that opens up a big can of worms from a regulatory point of view, because FDA at this point, they recognize that models may not be stationary, and when the FDA qualifies a model, it's locked in. And they're struggling with uniform guidance for how can vendors update models without going through the cost of a regulatory review. And at this point, they're kind of vaguely pointing at processes by which people would go through some sort of they're taking on themselves to validate the performance of a model that's updated. But this is the details of how this will eventually fall out, still a work in progress. But I do think we need to have a world where we recognize models need to continually learn. Look, physicians do that. That's what continuing medical education is. Physicians don't stay stagnant. They have to keep learning as cases and equipment evolves. So do our models. So I do think that's going to be an important area to work on.
Okay, thank you. So next question comes from my former colleague, Dr. Harsh Agarwal. So the question, first, thank you for the great presentation. And given the AI algorithm for every upstream and downstream applications are continuously evolving, what key points FDA and Radiology Society look for to assess the algorithm as ready for clinical use? How do you see the development of these standards?
Yeah, I think that this is going to be a dynamic, evolving area. I have become increasingly interested in policy around AI, and I've been working with FDA to understand, like, where are they now? What do they need to improve their policy? I do think that there needs to be better regulation around this, more clearly defined, especially related to the issue of local refinement, recognizing that it has value, but how would this be regulated? What are best practices? And FDA is looking for data. So I think that what's really critical is to generate data around the problem of generalizability, the need for post-marketing surveillance. We need data to show to what extent this happens, and the benefit of making model changes, and develop best practices for how would that work. FDA is not going to come down from the high mountain and declare. They're going to develop their guidance based on published work that the community does. So that's why I think this is an incredibly important research area, to generate the data to give the information that the FDA needs to improve its regulatory approaches to AI. It's such a rapidly moving field. They're underfunded, and algorithms, like 110 of them, it's like it was like half that many last year. So we need to develop best practices, and importantly data that's going to prioritize, okay, what needs to be done from a regulatory and policy point of view first to avoid potential harm. I think there's also a need for education. Radiologists are still worried about being replaced, and they should be more worried about being replaced by algorithms that are not as good as them, because there's a potential patient harm. So, I don't see radiologists being replaced. What I do see, though, is radiologists, as they become educated, to be careful consumers of these products. We don't even have metrics in place for how do you make a decision of whether to adopt one in your practice. What should you measure? What should you do? I mean, that's the first step. There needs to be local evaluation. There needs policies around that. How do you do that? Practices. So these are important areas of focus of mine currently. I think that's what needs to happen, in short order.
Okay, thank you. I think it's kind of a consensus the society is achieving. Those radiologists better informed by the AI, equipped by the AI, will outperform the others. Right.
Mm-hmm.
I heard also FDA is kind of also developing tools for assessing the AI tools. Maybe they need an AI algorithm to approve those other AIs. Okay. Yeah. So we have quite a few questions there, but I don't think we have time to go through that. Sorry for. Question actually. Marius, do you guys have any final question to Dr. Rubin?
Oh, Marius, do you have a question? If not, I can go.
Sure. I was actually just telling Dr. Rubin that I truly enjoyed the presentation, but I'd rather leave time for the Q&A. You were saying there are lots of questions that are coming for him. I'd rather leave time for that than taking over.
Okay. I mean, maybe I can add a quick question about the relation of pathology and radiology, right? The fuse of it, and in the context of AI, what would you envision there at that intersection?
Yeah, that's huge. That's huge. I mean, but pathology and radiology have always been very, very closely aligned. Many practices have radiology pathology conferences in domains like breast cancer and bone cancer. You need to have the two put together to even establish a final diagnosis. There's plenty of examples where the pathologist isn't always the arbiter of the final diagnosis. And so rad path correlation is how radiologists learn radiology, by correlating with pathology. So now just imagine, rather than the human being doing this, because it's always was a manual process, you have the computer doing that, taking the pathology, integrating with the radiology, and doing that correlation and pushing that up to the radiologist to help them understand the radiological findings that underlie the pathology. I'm just waiting for an electronic textbook to come along that just integrates these two and helps just even teaching. But in practice, to me, the most exciting dimension of this is if again, it's limited by data sets, but if we have a large data set, and you can do machine learning to find radiology features that correlate with the pathology, then you've basically got a non-invasive biopsy potential of radiology. And there have been a number of exciting works doing this, particularly in the cancer space, to recognize cancer subtypes based on the imaging features. The whole field of radiomics is sort of about that, learning to identify pathological features, particularly disease heterogeneity, from integrating data sets of radiology and pathology. I'd have to say it's like, I'm very excited about that. But even beyond that's histopathology. There are these new pathology domains coming online, codex, where now we've got spatial information with multi-channel expression of protein markers, which now you can correlate with radiology and do similar things. So we have the more exciting biology coming our way, potentially revealed through radiology by integrating those data sets. But it's going to start with having sufficient data. But I'm very excited by the prospects of work in that space.
Exactly. Thank you.
And one thing I'll say that holds it back, while almost every radiology practice is digital, I think it's like 15%-ish of pathology practices are digital. At Stanford, we recently, in the last year, went all digital. So until we've got a critical mass of pathology practices that are all digital, we'll be a little bit data hungry for a while. So that's something that will take some time
to build this.
Yeah.
Good to know the number. I didn't realize actually there's only like 15% there.
Yeah. A lot of it has to do with economics. Radiology went all digital because film was expensive and the number of images kept exploding, so they had to go digital. Pathology, the number of slides isn't exploding, and pathologists can do just fine with a microscope. So the push, what's really pushing pathology to go digital is as pathology practices start encompassing more and more sites, it becomes costly to send pathologists out to all the sites. And so digital pathology is a way of centralizing pathology reads. It's really that which will push it along. I was hoping the computer applications for automated detection, diagnosis, et cetera, would help, but I think it's more being pushed by geography and multi-site settings.
Excellent. Thank you very much. Yeah. So we are a little bit over time.
Okay.
I'd just like to thank you again for the great presentation. Very informative, mind-blowing talk. Thank you very much.
Okay. Thank you, everyone. Have a good day.
Thank you, Dr.
Thank you. Bye, everyone.
Thank you. Bye-bye.